So a little review of prime factorization. Prime factorization is when you break up a number so that all you have are multiples that are all prime numbers. So 24, we could break it up to be 4 times 6 to begin with. And then 4 is 2 times 2. 6 is 3 times 2. And in the end, those are all prime factors, 2 times 2 times 2 times 3. We could write that as 2 cubed times 3, and this would be a prime factorization. You don't have to use 4 times 6. What else is 24? 24 is also 12 times 2.
So you can collect like terms and it would still count as a prime factor?
Well, we're not collecting like terms, but you could break up 24 however you would like.
Like with the 2.
Yeah, there's 2 times 2 times 2 becomes 2 cubed. That's still prime factors, yeah. Can I break up 12? 2 is already a prime number, but I can break up 12. What's 12? 6 and 2. So then we can go 6 times 2, and I still have times 2. And can I break up the 6? Yes. It's 3 times 2, and I still have times 2 and times 2. You get the same answer. So if you're wondering, what happens if I don't pick the right numbers to start? There are no right numbers to start. You could choose anything. And some things that come in handy. How do you know if something divides by 2?
If it's an even number.
If it's an even number. So that's when I see 24, I know already I can divide it by 2. Now that's going to come in more helpful when you start off with a much bigger number. Okay? Here's a bigger number, 144. And I'm going to introduce to you a factor tree. Now the factor tree does the same thing that our method that we did before. I sometimes find, though, that in the method we did before, sometimes students, when they say, oh, 12 is 6 times 2, they forget to write the times 2 that they had before. And then they, oh, 6 is 3 times 2. Now they forget that, oh, I had these extra times 2 times 2. They still have to be there. So we introduced something called a factor tree, which can help you not forget. So first of all, we have to say 144. What makes 144? 12 times 12. So you break up your two factors, 12 and 12. And every time you break up a number, you make branches. And that's why it's called a factor tree, because trees have branches. And this has branches. Right? If these look like chicken legs to you, then you can call this a factor chicken. But we're going to call it a factor tree. Okay? Because these look like branches. Can you break up 12? What's 12?
6 times 2.
6 times 2. So this one can be 6 times 2. This one can be 6 times 2. Can you break up any of those numbers? Yes. The 6 is 2 times 3. And this 6 is 2 times 3. And once we get down to the bottom of the branches, where no more numbers are composite numbers, all the numbers are prime numbers, we are done. So we can take our answer and say 144 is equal to, and we have to look at all the bottoms of the branches. How many 2's do I have? 4. So 144 is 2 to the exponent 4 times, how many 3's do I have? 2. And this is the prime factorization.
If we wanted to, could we fold the two other 2's down to make it in line with the 2
If you wanted to, yeah, you could just branch this down like this, you mean?
Yeah.
Yeah. Although generally, some of the numbers that get big, you'd be pulling numbers down forever. Because this next one, oh,
We actually like have to do it.
yeah.
Wow.
So we have a very big number. And in this number, you might right away say, well, because it's even, I can divide it by 2. So here I'm going to put my 2, and here 1,323. And I'm going to introduce to you another thing for figuring out numbers. How do I know I can divide that number by 3? Does anybody know the trick for dividing by 3? Couple? Yes. So the trick for dividing by 2 is the last number is even. The trick for dividing by 3, to tell if a number can be divided by 3, is if you add up all the digits, 1 plus 3 is 4, plus 2 is 6, plus 3 is 9. And if that answer that you get, you can divide by 3, it means that this can be divided by 3.
Does that scale forever? Or does that work for any?
That works forever, no matter how big it is. It also works for 9. So I can tell you right now that 1323 divides by 3. It also divides by 9. Because 1 plus 3 plus 2 plus 3 is 9, and 9 divides 9. So this strategy works for 3, and it works for 9. What is it equal to? 441. You could use your calculator for that. Whew. 441 adds up to 9, which means we can divide it by 3 again. Can you see why I wouldn't necessarily like this too? I'd have to just keep writing it. It's nicer, just keep it clean. 441 divided by 3 is 147. What's 1 plus 4 plus 7? 12. Does 12 divide by 3? Yes.
Are there rules for other numbers?
There are. I just learned a new one this summer. I was very excited about it. It's not a very nice one, and so I keep forgetting it. But I'll try to show it to you. Okay. 147 divided by 3, what would you get? 49. What times what is 49? 7 times 7. Are those all prime numbers now? So if we take all the bottoms of our branches, we have that 2,646 is equal to, how many 2's do we have? 1. How many 3's do we have? 3. How many 7's do we have? 2. This is the prime factorization. What I like about the prime factorization is I can put any combination of those numbers together. Thank you. So if I put any combination of those numbers together, for example, 7 squared is 49. 3 cubed is 27. 27 times 2 is 54. 54 times 49 is 2,646. Which, me liking numbers, I think that's cool. Okay? I could also have put the 2 and the 49 together to get 98, and that is 27. So 27 times 98 is 2,646. And if you can break a number down into its prime factorization, you can start to figure out all the different pairs of numbers that multiply to give you that number, which I think is neat.